In this video, we are going to talk about normal distributions and what it means to standardize a value. So let's get started. In this example, we're talking about IQ scores. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. And they're asking us to find some probabilities associated with different values. So if we were to look at this graph, the mean of 100 means that that's where that peak is for each of these pictures. Now that first one has everything shaded to the left, so we're trying to find the probability x is less than 118. And the reason we're going to use less than is because it's shaded to the left, and the reason we're using x is because this is an IQ value. It is not a z-score. But we could standardize this, and what that means is apply the z-score formula. So the z-score formula is the x value minus the mean divided by the standard deviation. So I'm going to get 18 over 15, and 18 divided by 15 is 1.2. So this is equivalent to saying find the probability that z is less than 1.2. Okay, remember that z-score tells you how many standard deviations away from the mean a particular value is. In this case, 118 is 1.2 standard deviations above the mean. So if I want to find this probability value, I'm going to go back to SALT. I'm using a distribution calculator, and let me resize this. So I found the mean. I standardized a score, which means I could look at the standard normal distribution. I want to know what's going on in the left tail. My z-score value was 1.2. And I'm going to get a probability of 0.8849. So that's what we would write on our notes over here. Okay. But what's nice with technology is that we no longer have to think about that z-score. We could actually just type in all the information. So let me show you that. So they told us the mean was 100 and the standard deviation was 15. We want to find the probability we are less than 118. And you can see that it's going to standardize that for us. It's going to pop out that z-score value of 1.2. And it's going to give us that probability of 0.8849. So you've got a couple of options here. Let's do another one. Let's look at number 6. We want to find the probability that we are greater than 91. So what's the probability a randomly selected person would have an IQ greater than 91? I'm going to use technology. The mean is 100, the standard deviation is 15. Now we're looking at greater than, which means right tail. And we're looking at greater than 91. And we're going to get out 0.7258. So there's a 72.58% chance. And it also told us what our z-score was. So you can see how here's our mean at 100. Our z-score is negative 0.6, which means that this value of 91 is 0.6 of a standard deviation below the mean. Okay, let's do a couple more. Let's look at some of these. Now they're asking us for a z-score that's associated with a particular value. So I'm looking at the probability. I am shaded to the left, so less than. And I'm looking for this x value. I'll call it A. We don't know what it is. But I know that probability is 0.9918. So let's type in what we know. So we know the mean and the standard deviation. We are looking at the left tail, and we know the probability is 0.9918. Type that in. and we'll get our X value here. Our X value is about 135. So this would be 135. There's your cutoff score. Okay, if we look at number 10, we could do the same thing. This is greater than. And that probability in that right tail is 0.1587. Pull up our technology. Mean standard deviation stays the same. We're choosing right tail. That probability is 0.1587. And we can get that X value, which is about 115. So there's your cutoff score for that. Let's look at a word problem. Engineers want to design seats in commercial aircraft so that they are wide enough to fit 99% of all adults. Assume adults have hip widths that are normally distributed with a mean of 14.3 and a standard deviation of 0.9 inches. We want to find P99. That is going to be the width that separates the smallest 99% from the largest 1% of the population. So let's draw a picture of what's going on. So here's our 99%. That's going to be in your bottom. There's your 1% here. And we are looking for that cutoff score. What would that be? Okay, notice we're shaded to the left and 99% is shaded to the left. So we're going to go over here, left tail. Our mean is 14.3 and our standard deviation was 0.9. And the area in that left tail is 0.99. So that cutoff score that separates that bottom 99% from that top 1% would be 16.39 inches. And that's an X value. That is not a Z-score. The Z-score associated with that would be about 2.33. And let's look at one more. And this is where you may want to pause the video, try it, and then come back. So human body temperatures are normally distributed with a mean of 98.2 and a standard deviation of 0.62. According to emedicinehealth.com, a body temperature of 100.4 degrees Fahrenheit or above is considered to be a fever. What percentage of normal and healthy persons would be considered to have a fever? So we want to find the probability that a randomly selected person has a temperature greater than, or we could say greater than or equal to, it doesn't really matter. Greater than 100.4, sorry. Lost my train of thought there for a second. So we're going to type everything we know into our technology. Normally distributed, our mean is 98.2. Our standard deviation is 0.62. We are shading to the right because we want greater than 100.4. And since this is a continuous distribution, remember it doesn't matter if it's greater than or equal to. And we're going to type in 100.4 as our X value. And that probability is going to be really small, 0.0002 if I round to 4 decimal places. 0.0002. So as a percentage, that would be less than 0.02% of the population. B, physicians want to select a minimum temperature for requiring further medical tests. What should that temperature be if we only want 2% of healthy people to exceed it. So let's draw a picture. So 2% is going to be in that right tail. 2% as a decimal is 0.02. And we are looking for that cutoff score there. What would that be? So same mean and standard deviation. This time we're in the right tail. So I've still got right tail selected here. And I have the probability 0.02. And that cutoff score is going to be 99.47. So there's our probability.